Hello there. So in this exercise we got a set V that is defined over the real pairs that have this structure. That means 1 in the first coordinate, and on the second coordinate you got just any real number. Okay, so this is the structure of the elements of this set V, and in addition we got two operations, the sum operation that is defined as follows. Here we got two elements of the space V, and when we sum them up we keep the first coordinate the same. That means that we just put a 1 there, and then we sum the second component of each of these vectors. One important remark of this is that this x and this y are both real numbers, and the sum of two real numbers is again a real number. That means that these have the same structure, this whole vector have the same structure as a vector on V. That means that this vector is an element on V, and this helps us to demonstrate one of the axioms of vector spaces. That is the first one, that is related with the closeness of the sum operation. In the same way, when we define here the scalar product, we got that in a scalar, just to remind you that a scalar is just a real number. It's basically a number that we are multiplying to this vector. And when we multiply a scalar via vector, we keep the first coordinate the same. That means that we just put a number 1 there, and then here we multiply in the second coordinate. Here again, k is a real number and y is a real number. That means that both, when you multiply both, you have again a real number. So this also satisfies the structure of a vector in V. That means that this is a vector in V, and therefore we are proving the sixth axiom of the vector spaces. So the point of this exercise is to prove that this space V, together with these two operations defined on the scalars on the sum of vectors, corresponds to a vector space. So let's start. So after showing some of the axioms already, the 1 and the 6th, let's start from the second one. So the second one, we need to show this commutativity property of the summation. So for that we're going to consider vectors of this form. U is going to be 1x, V is going to be 1y, and W will be 1z. And these three vectors is clear that are elements on this space V. So let's show this property. So U plus V is equals to 1x plus 1y, and this, when we sum them up, we obtain the first coordinate will remain the same, and then here we got x plus y, and that's it. And on the right hand side of this expression we got U plus, here is V. So here we got V plus U, and this is 1y. Yes, here is y plus 1x. And when we sum them up, we got 1y plus x. But these two here are real numbers, so we know that the summation in the reals commute. That means that this vector is also equals to 1x plus y, and then we got that these two vectors are the same. Therefore this property is satisfied on this space. The next property is the associativity property. So for that we need to consider three vectors. So let's start from the left hand side. That means U plus V plus W. This equals to 1x plus U plus W is going to be 1y plus z. And then we sum these two vectors. So we obtain 1x plus y plus z. And then the right hand side of this expression will be U plus V plus W. So this is equals to 1 x plus y plus 1 z. And then when we sum these vectors, we obtain 1 x plus y plus z. And you can see that both of these vectors are the same, so this property holds as well. The next is related with the zero vector. So the zero vector is a vector that when we sum with any other vector on this space V, we obtain the same. This is just an intermediate step that is related with the commutativity property. So it's enough to show that 0 is an element of B, and that if you pick any vector u plus this vector, you obtain the same vector. And in this case, this zero vector is defined as 1, 0. You may ask why we are not putting 0 as the 0, 0 vector. Well, the point is that if we put here a 0, what happens is that this vector no longer is no longer part of this set V, because the structure of the vectors in V satisfy the property that is the first coordinate is equals to 1 and the second is any real number. So for that, the zero vector should be 1, 0 and non-zero, 0. Okay, great. So let's check this. So u is equals to 1x plus the vector 1, 0. This is the zero vector, this is u, and when we sum this, we obtain 1 x plus 0, and this is equals to 1 x, which is equals to u again. So yes, the zero vector exists on V, and it holds the property that we should expect. So when the zero vector defined, we can find the inverse. We can say that the inverse lives also in this space V. So given any vector, we need to find a unique inverse such that when we sum these two vectors, we obtain the zero vector. So in this case, u is equals to 1x, and minus u is going to be equal to 1 minus x. Again, here you may ask why we are not putting minus 1 minus x. Well, that's because if we have here minus 1, this is no longer part of B. It's just any other vector. We need to have here a 1 to be part of B. So from that, here is just a negative, it's just the inverse number of x. So this is again a real number, so this is part of B. So let's show that this property here holds. So that's not that hard. So we got 1x plus 1 minus x. This is the vector minus u. This is the vector u. And this at the end is just 1x minus x. And this is 1, 0. And this is the zero vector. So yes, the fifth axiom is hold in this space. Now let's keep going with the scalar product properties, axioms of vector spaces. So here k is just a real number or a scalar. Okay, so k is just a real number. We know how is defined the scalar product. So u plus this left hand side of this expression is equals to k u x plus y, and then we multiply this vector by a scalar, and remember to keep the first coordinate the same, and k that times x plus y. Okay, then these elements here are real numbers, so we can distribute the k among x and y. So we got 1 kx plus ky, and look, this is the same as the sum of two vectors. These vectors are 1 kx plus 1 ky, and this is the same as ku plus kv, as expected. So yeah, the seventh axiom holds. let's keep going. Now we got the eighth axiom. So here we got, here in this case, k and m are real numbers. They are both scalars. So k plus m times the vector u. In this case, k plus m act as a one scalar. So we got here k plus m times the vector 1x, and when we multiply this scalar by this vector, we obtain 1 times in the second coordinate k plus m times x. And here happens something similar to the previous example. All these are real numbers, so we can distribute the x on the parentheses, and what we obtain is 1 kx plus mx. So this is the sum of two vectors, the vector 1 kx and the second vector 1 mx. But this is just ku plus kv as the eighth axiom expect. So yes. The ninth axiom, we need to consider the multiplication of scalars. So here we got mu. In this case, mu is equals to 1 mx, and then we multiply k by this vector and we obtain 1 k mx. And on the right hand side of this equation, we got km acting as a one scalar. This is just one scalar times the vector u, and this is just km 1x, and when we multiply by this vector, we obtain 1 kmx. Both vectors are the same, so this property also holds. And finally, the identity. So here, one is the identity on the real, so this is the identity of the scalars. So when we got 1x, this is equals to 1 times x, but this is just 1x, and this is equals to u. So yes, it also holds. So from all these 10 axioms that we have shown that this space V satisfy, this implies that V is a vector space.